we have talked about vectors and even dual vectors, which were the one forms. So let's extend that idea and talk about something that is really wonderful, right? And that is something that we call tensors. So before we get to the definition of a tensor, let's actually start with discussing few of their properties, right? So the first one being that tensors represent physical quantities that are invariant. However, if you are given an explicit coordinate representation, it will typically have components that will transform, right? Now, moving on to number two, and well, it is that tensors live in a flat tangent or cotangent spaces, or it could also be the tensor product of tangent and cotangent spaces, but at each point in spacetime. Okay, so in terms of the labeling scheme for a tangent or cotangent, what we have is something like, if you see something like 0 comma 0, this tells you that we have scalars, right? And if you see something like 1 comma 0, that is what we call vectors. And so then you can also see something that is 0 comma 1, and well, of course, that would be dual vectors. Then you could have 0 comma 2, and that thing is your metric tensor, right? So it's your eta mu nu. And well, if you shift 2 over here, that is, if you write 2 comma 0, right, what is that? Well, that is simply the inverse of the metric. So inverse of metric, and what would that be if you were to write eta mu nu? Well, it would be eta mu nu, right? So here you have covariant and here you have contravariant. Now, in general, we could have a mu nu mixed tensor, right? So, well, I wouldn't say mixed tensor, let's just say mixed indices for now, right? So, in general, we could have mu nu mixed indices. So let's consider an example very quickly. So think of a tensor that is t mu nu alpha lambda beta gamma and sigma. Now this thing, this object over here, this is a tensor, and it is a 3-4 tensor. Now you might ask me, why is it a 3-4 tensor? Well, it has 3 upper indices and it has 4 lower indices, right? Okay, now though we will usually only deal with components of the tensors, remember that the full story actually is that you have t is equal to t mu nu alpha lambda beta gamma sigma and the basis vectors e hat mu tensor product with e hat nu tensor product with e hat alpha, right? So this is for these two, right? So we are in the ordinary vectors right now. So these are your ordinary basis vectors. And then for these ones, the lower ones, you go into the dual vector space, or one forms, and there you have your basis vectors w hat lambda, a tensor product w hat beta, tensor product w hat gamma, tensor product w hat sigma. So I got these from these lower indices, right? Okay, so now let's define a tensor, right? So, well, there is a usual definition of a tensor, and then there is the one that is a bit unpopular, but a much more fruitful definition. So let's first write down, or let me just first tell you what is the usual definition. So it goes something like that: a tensor is an object, or a tensor is something that transforms, and wait for it, like a tensor. Now, if you hear this, right, or if you have heard this, or if this is the definition that you know for a tensor, you would probably go something like this, right? Or something like this. I mean, you are using the word tensor in the definition of what you are defining, that is a tensor. So, I mean, to me, that does not seem very clear. The definition of a tensor that I prefer, or the unpopular but a much fruitful definition, is something that says that a tensor is a multilinear map from a space of vectors. So you have bunch of vectors in this space, and it's a map that takes you from this space of vectors and dual vectors, and it takes you into the reals, right? So into the real space, real coordinate space. What that means is simply that if I have this thing, that a tensor on v w w w, where v's are your ordinary vectors and these are your dual vectors, right? It takes you, or it gives you a number. It maps to a number, right? Now, this definition for a tensor is a much more clearer definition to define a tensor. And this definition is born out of something that you call a well-defined tensor. So then the naturally occurring question is, what the hell is a well-defined tensor? So what is that? Well, a well-defined tensor is something that, you could write it as t mu nu alpha lambda beta gamma, let's say delta, right? We're just using any indices, right? You could use, and lambda v beta v gamma and v delta from this. And then in the dual vector space you have w mu w v w nu and w alpha, and we already know that this thing belongs to the reals. Now again, a well-defined tensor is something that is like this, but what is so special about this thing? Well, if you notice, or if you look long enough, you will immediately realize that this has no free indices, right? All the indices have been used. You could compare and contrast this with something that we call a starving tensor. So let me just write this down over here. compare your well-defined tensor with something that is called a starving tensor. And what a starving tensor simply is something that you can write t mu nu alpha lambda beta gamma delta, and v lambda v beta v gamma v eta w mu w nu w. I'm sorry, I'm writing this completely wrong, forgive me. Let me just rewrite this thing over again, right? Again, I'm sorry, it is v lambda v beta v gamma, right? And then you have w mu and w nu. So you skip this alpha, and that is why it's called a starving tensor. So you have to feed it one more indices to make it a well-defined tensor. But right now it is missing one of the indices. And then this thing would simply be equal to f alpha and delta, right? Because those are the indices that we are missing. We don't have an alpha in this one, and we don't have a delta for the ordinary vector space, right? And similarly, we have another one that is called overfed tensor. So you could think of this tensors like it is eating these indices. So if you do not give it these two indices that we already have in this tensor, you do not provide it from this vector space, it is a starving tensor. And now if you will see in the overfed, you'll see that you provide it with another extra index, right? So let's see, t mu nu alpha lambda beta gamma delta. Now the vector space is v lambda v beta v gamma and v eta. Now this one is the overfed one. And then you have w mu, w nu, and w alpha. This thing would give you h eta, right? So now you will, from here, now you will see that all of the work that we had done previously on vectors, defining vectors, playing with vectors, and dual vectors as well, it pays off big time now. So let's look at the transformation of tensor components, which is determined by their index. So you could say that you have a C and it transforms to C prime, but it is C because it is an invariant, right? So say you have a vector v mu, it transforms to v mu prime. What was that? That was, you had this transformation object mu prime mu v mu, right? And likewise for the dual vectors, w mu transforms as w mu prime, which is simply lambda mu mu prime and w mu, like this, right? Okay, so now look at the tensor t mu nu. How would this thing transform? It would transform as t mu prime nu prime, but what would that be equal to? Well, simply if you remember all the work that we did on vectors and dual vectors, we built the transformation laws and those would be the same. So, well, you could see now this thing would be lambda mu prime mu lambda nu prime nu t mu nu. And this again, it comes from the transformation laws that we built in the video on vectors, right? And likewise, if you have a mixed tensor, which is defined as, or it's written as h mu nu. So you have one index in the upper part and you have one index in the lower part. That is called a mixed tensor. So this thing would transform as h mu prime nu prime, and that would simply be equal to lambda mu prime mu lambda nu prime on h mu nu, right? And well, we could go a bit further and we could also write down a tensor that is a covariant tensor. So we would have index in the bottom, and that would be, or that would transform as g mu prime nu prime is equal to lambda mu prime lambda nu prime g mu nu, right? And remember, if you want to use the matrix multiplication for all of this, right, we were able to write those, because to use matrix multiplication you need to get the repeated indices adjacent, right? And we used this thing that lambda nu prime nu is equal to lambda nu prime nu transpose. Well, you could use this and use this thing that lambda nu prime is equal to lambda nu prime nu inverse, right? So if you shift the indices, these two indices, and you take the inverse, it would be the same thing as the one that you started with, right? So with this, then with these two, we have lambda nu prime is equal to lambda nu prime nu inverse and the transpose of this from these two set of equations. So then we can say that lambda, simply lambda is equivalent to lambda mu prime mu or lambda nu prime nu. If we can do this, which we can, then we can write down that lambda and tensor in between this, lambda transpose, something that is like this, would simply be the transformation of your tensor t prime, right? And likewise we would have for let's write this one down. Let's say we have a tensor that is this h, which was over here the mixed tensor. If I were to sandwich this between lambda and lambda inverse transpose, I would get the transformation h prime, right? So these are some of the important things that I'm writing down. So hopefully you're paying attention, right? Now if I were to sandwich g, which is a covariant tensor which has indices in the bottom, and I sandwich that in lambda inverse transpose and lambda inverse, right? This would give me the transformation of the covariant tensor G, right? Okay, so now that we have many tensors, so you have seen all of these tensors that we could write, to consider, we should be careful with some of the special ones, right? So let's say take the usual metric tensor that we have, say eta mu nu. What this thing does for you, or this object it does for you, is that it takes an upper index and it takes it to the lower one. Now this upper index is in the tangent space and the lower index is in the cotangent space. So let me write this down and try to explain this thing to you properly. So you have eta mu nu t nu So eta mu nu is acting, or we are multiplying it with t nu. It simply takes your index over here. So what it has done for you is, consider if this t was just a vector, right? As we had been talking in previous videos on vectors and dual vectors. Consider if this was just your vector. What eta mu nu did is it transformed, or it converted your vector to a dual vector. And if you remember, vectors lie in the tangent space, whereas this a dual vector is in the cotangent space, right? And likewise, if I had eta mu nu, it would do the vice versa, right? So now note that both of these eta mu nu and eta mu nu are symmetric. So what that means is that if I have this eta mu nu, it is the same as eta nu mu, and this eta mu nu is the same as eta nu mu, right? Okay, so however, a very important distinction over here is the following, that if I have eta mu nu on a tensor t nu, it gives me t mu, right? As we have just seen over here. And if I have some m mu nu on t nu, it gives me h mu as well, right? Now over here, this is a tensor, and the difference between this, or let's say in both of these cases, you can see that the upper nu index dropped to a mu index, right? You can see that, right? This upper nu index had dropped down to a mu index. Same over here, right? But only for the action of eta mu nu, this one, does the result correspond to the dual of what you start with, which is this thing. However, in this case, you can see that we have changed. The tensor has changed, right? So this thing is not the dual of this thing, right? So that's very important to note. Okay, so for a general tensor like this one, that is m mu nu, right? The above result is actually a different quantity, right? So as I mentioned, this thing is a different quantity. This is not the dual of this t nu, right? It's not the dual of that, and that's why you can see that we used a different letter over here, h. Okay, so well, we can go a bit further and let's play a bit around. So let's just consider some eta on eta action, right? So what I mean by that is, take eta alpha mu and take another eta, so that would be eta beta nu, and let's take another eta, say eta mu nu. Well, this thing, if you use the contraction of the indices, this just gives you eta alpha beta, right? So you can see nu and nu will contract from this one, and from this one mu and mu will contract, and all you're left with is eta alpha, and well, you have beta over here, so that would come over here. So that's how we get this. Okay, so well, let's get rid of all of this that I just wrote down. Okay, let me see. Yeah, okay, now let's simplify this a bit, and let's see what we have. Eta alpha mu eta mu nu, right? So we have just moved this over there, and we could then have eta beta nu, right? And this thing is still, it is equal to this one, that is eta alpha beta. So from this now, if you look at this thing, what is this? It is simply the delta function. That would be delta alpha nu, right? Okay, so and then we have this eta beta nu. So if I have this thing, what is this equal to? Well, if you can see, first of all, this is equal to this thing, eta alpha beta. Now this over here would be equal to eta beta alpha, right? Which is again, from this it is equal to eta alpha beta. So what have we just proved is that this is indeed a symmetric tensor, right? Okay, so well, then you can consider or ask, what about something that is eta mu nu, right? What about this thing? Well, let's evaluate this. Eta mu nu is equal to delta nu, right? This thing is equal to this, and if I well, if I use the Einstein's summation convention, this thing is simply delta 0 0 plus delta 1 1 plus delta 2 2 plus delta 3 3, right? And that's it, because we have this eta in space time. So this thing would simply give you what? Well, if you remember the delta function, delta mu nu, it gives you +1 for mu is equal to nu, and it gives you it gives you nothing, or it vanishes when mu is not equal to nu. So using this, then we can write down this thing as, this thing would give you +1, this thing would give you +1, this would also give you +1, and this would also give you +1. So 1 plus 1 plus 1 plus 1 is 2 plus 2, 4, right? So you could say that this thing is simply giving you the dimensions of your space-time, right? Okay, now we know the coordinates x mu transform like vector components v mu, right? So then we can ask, what about this derivative, that is partial over partial x mu, right? What about this thing? So well, let's say you have this partial over partial x mu on x nu, right? What would that be equal to? Well, this is again, it is equal to a delta function with nu and mu, like this. But what is this then? It is again using this definition of the delta function. It is, well, it is just a number. So you can write down a number. So what does that mean? That means, or that is telling you, that partial over partial x mu must transform oppositely of x mu, right? So what is that? That mathematically, that is that we have partial over partial x mu is partial mu, right? So that is the reason that we write this for this, when we have this mu in the upper index of x, we write this partial mu as this, where you have mu in the lower index of this partial symbol, because partial over the partial x mu should transform oppositely of x mu, right? And so we can say then this is a dual vector, right? Okay, so now we have all of these things. Let's move on and talk about what we can make with these tensors. Well, the first thing you should consider is, well, tensor equations, right? Writing down equations in tensors. So the physical world, or first let me write this down, that we are specifically talking about tensor equations, right? And so the physical world has no predetermined absolute coordinate system. Either it's inertial or otherwise. There is no predetermined absolute coordinate system, right? The truly fundamental laws of physics should be built out of such quantities which are at least invariant under transformations that are connecting inertial frames, right? And that is relativity. So this simply means that they should be built out of tensors, right? And so nature demands tensors, and so we have then we have tensors to understand her, right? And so that is why I mentioned that tensors is one of the most wonderful idea in the beginning of the video, right? Now, but if we are working only with tensor components, how do we see that an equation, a tensor equation, is invariant? So, well, we could use only scalar equations where you have A is equal to B, which is A prime, which is then equal to B prime, where A prime has to be equal to A and B prime has to be equal to B. But, well, what we want is something or more interesting options. Say something like we have this equation, you have F equals ma, right? Or F equals the rate of change of momentum. So for a more general scenario, when working with components, we just need to make sure that the equation is covariant. What that means is that each side of the equation transforms in the same exact way. What I mean by that is, consider we have A mu nu, which is equal to B mu C nu alpha, and this is alpha, D alpha, and it transforms as A mu prime, that is not mu prime, mu prime nu prime, which is equal to B mu prime C nu prime alpha prime D alpha prime. Now this thing is then, this thing, it becomes, well, remember we have the transformation matrices or the transformation objects as lambda mu prime mu, lambda nu prime nu on A mu nu. This is equal to this thing, right? Okay, and then this is equal to, well, this one, right? But for this one, what is this equal to? This thing, well, that is again equal to this transformation matrix acting, so that's mu prime, that does not look like mu prime, yeah, mu prime mu lambda nu prime nu B mu C nu alpha lambda alpha alpha prime lambda alpha prime alpha D alpha. But then this thing, it just gives you the identity, right? because it is lambda matrix and the inverse of lambda matrix. So that is just identity, right? So it's this is just lambda inverse, right? Okay, so then what this is simply that you have lambda mu prime mu lambda nu prime nu on something, on tensor, is equal to lambda mu prime mu lambda nu prime nu on another tensor, right, in generally. So then we can we restore the complete expressions with basis vectors and dual basis vectors. The complete expression will actually be invariant. That is what you can see from this. So, well, index symmetries should also agree that, well, say you have, let's go down over here. You have F mu nu, and we know this electromagnetic strength tensor is equal to partial mu a nu minus partial nu a mu, correct? Well, if you look at this thing, well, you have F mu nu is equal to equal to a negative F nu mu. That just means that it is anti-symmetric. And for this one, we have mu nu equals negative nu mu. Right, so to get more appreciation for the power of tensors, consider the very well famous equations that are the Maxwell's equations. So let me write this down. Maxwell's equations. What are the Maxwell's equations? Well, we have del cross B is equal to, or let's write it like this, minus partial time derivative of the electric field E is equal to the current density J, and you have the del dot E, the divergence of E, is equal to rho. We have del cross E, the curl of E, plus the time derivative of the magnetic field, which is equal to 0. And well, we have this del dot B, which is equal to 0. So over here we have we have three equations from this one. We have only one equation from here. We have again three equations from here, and we have one equation from here. So in total, the total Maxwell's equations are, let me write this like this, right? Okay, so the total Maxwell's equation is just the sum of this, which would be 8 equations, right? So there are 8 total Maxwell's equation if you open them and write them down. Now, while it is obvious that these equations are invariant under rotations, it is definitely not obvious that they are invariant under boosts. So introducing J mu, which would be simply, if you remember the current density, the temporal component, that is the time component, is rho, the charge density, and then we have the spatial components as J1, J2, and J3, right? And we have we introduce this 0,2 field strength tensor. Field strength tensor. What is it? Well, let me write this down very quickly. We have F mu nu, and that is why I wrote 0,2. So when in the beginning I talked about the labeling scheme, we don't have any indices in this upper place, but we have 2 indices in the lower place. So that's why it's a 0,2 field strength tensor, right? Okay, so this is just equal to, well, it is 0 minus E1 minus E2 minus E3. Then we have E1, E2, E3. We have 0, B3, and we have negative B2. We have minus B3. Again, this is not the power, and I hope you are obviously you know that, right? This is just the components for these. So E1 corresponds to EX, E2 corresponds to EY, and E3 corresponds to EZ, and likewise. So yeah, I don't know why I'm telling you this. I'm pretty sure you already know about that. So yeah, then we have 0, B1, B2, we have minus B1, and we have 0. This is your 0 to field strength tensor. Then we have this equation that is partial mu f mu nu, and we have derived all of these equations in our series on the relativistic electrodynamics in tensor notation, right? There I have talked about field strength tensor, even the dual field strength tensor, and a lot of things, right? Well, we have this thing is equal to J nu, right? Now, over here in this thing, we have 4 equations. So for 0, 1, 2, 3, right? Components. And we have another one which you might not know, but that is partial mu f nu lambda is equal to 0. And this also contains 4 equations. This thing comes from the Bianchi it comes from the differential forms and a lot of things. Well, we'll talk about this some other time in detail, but my point over here is that this also contains 4 equations. We have this combination of 0, 1, 2, 0, 1, 3, 0, 2, 3, and 1, 2, 3. Right? So we have total 4 from here, and we have total 4 equations from here. So in this, we have a total of 8 equations. So you can see that over here, we had 1, 2, 3, 4 equations. And we had, from those 4, we had 8 equations. But now we can simply, using the tensor language, we can just write down these 2 equations. And these 2 equations will give you all of the 8 Maxwell's equations, right? Okay, so now that we have expressed Maxwell's equations in terms of tensors or the tensor components, then we know that they are indeed invariant under all the lambdas, including the boosts itself. But recall that these equations, they predict a c, and therefore c, the speed of light, is invariant under boosts, right? Okay, so well, and this is all for this video on tensors, and hopefully you have understood a great deal of what tensors actually are and why are they very important to us, and why should you even appreciate the beauty of tensors. I hope you have answers to all of these questions from this video. In not the next video, but in one of the later videos, we will talk about tensors under some general coordinate transformations, and we'll talk about that in depth, right? So from here now, I could talk about I could tensorify the kinematics, right? But I have done that in one of my videos on proper time, proper velocity, and in one of those videos, right? So I would not be doing that in this series of videos. But of course, if you would like for me to actually go ahead and do or the tensorify the basic kinematics that we know, uh, you could well, you could mention that in the comment section, and if you really want me to do that, I will go ahead and I'll make a video on kinematics in tensors, right?